Okay, this video looks at gas chromatography. So gas chromatography works on very similar principles as thin layer chromatography. We have a mobile phase, that's a phase that moves, which is in the inert gas. Inert as an unreactive, it could be nitrogen or helium, something like that. In thin layer chromatography, the mobile phase was the solvent that was moving up the plate. And then we have a stationary phase as well. In TLC, the stationary phase was your silica plate or your aluminium oxide plate. Here, the stationary phase, the phase that doesn't move, is inside this column. So this line going around here, let's do a different colour so you can see it. Okay, well, this curved line, spiral line, is actually a tube, and what we call a column. And the column could be packed with different things. Sometimes it's packed with liquid, so it could be a very viscous, high density liquid, like a high density alkane, or it could be something like a solid, like an ionic compound packed in there. So the inert gas is under pressure, and so it pushes through the column and comes out at the detector. And what we do here is we take our sample and we inject it into the column, and it's pushed along by the inert gas. And different substances will get through this column at different speeds, because it depends on how much they are attracted to the stationary phase within the column. So if you've got something very polar and you have a polar substance inside the column, it'll take a long time to get out, because like attracts like, polar attracts polar. If you have something non-polar though, it'll come out very fast. But you could change the column, and you could put something like an alkane in there, which is a very viscous one that isn't going to leave the column, but some things that are non-polar will be attracted to that non-polar alkane and take longer to come out. When they do eventually come out, they get detected and it's recorded in a graph. So what we measure is the retention times. The retention times is the time it takes for the sample to go from being injected over here to detected over here, and that's recorded in a graph like so. So let's have a look at a couple of scenarios. If we had a column full of a highly viscous alkane, the alkane itself here is non-polar, so our stationary phase is non-polar. So if this is our mixture that we have a mixture of methanol, hexane and propane, the most non-polar out of those is hexane. That will take the longest to come out in the case of scenario 1. So it will be the third one to come out. It will have the longest retention time. The most polar one will come out first, which in this case will be methanol. That will have the shortest retention time. And propanone, whose polarity is between the two, will be the second one to come out. If though, look at scenario 2, and we change it and we put an ionic solid packet in there, rather than having the viscous liquids, that's very, very polar. So now polar things will take longer to come out of the column. So they have a long retention time. So in this case, methanol would have the longest. Hexane will be the first out because it wouldn't be attracted to the polar substance. And again, propanone is in between the two. So what you end up with is the graphs that look like this, and along the x-axis it says time there, more accurately it's a retention time from the sample being injected to when that component in the sample was detected. So what conclusions would I make from this graph? Well, it looks like this mixture had 3 substances in it. There are 3 peaks, so the mixture must have had 3 substances in it. Now these retention times do have the limitations, just like in TLC of RF values. There could be more than one compound under one of these peaks. This peak here could actually be 2 compounds, or this one could, or it could be 3 even. Okay, there's no way of knowing really, just from this experiment. So there are limitations. we can't identify something just from retention times because similar compounds have similar retention times. But let's say that these are three separate components, three separate substances. The area under each peak, so it's not the height of the peak, but the area under each peak is proportional to the concentration of each component. So judging by eye, this middle peak here looks like it's got the largest area. So that one would have the highest concentration in the mixture. This one would have the lowest. Now in the exam, they're not going to get you to actually integrate it and work out the exact area, but they could give you the proportional areas in some sort of format for you to compare, and then maybe do a calculation to work out what the concentration could be. So it's just important to remember it's the area, not the height of the peak.